Welcome to Tech Girl Kannada YouTube channel. Module 2 Stacks. Definition: stack operation, array representation of stack using dynamic arrays, array applications, polish notations, infix to postfix conversions, evaluation of postfix expression, recursion, factorial, GCD, Fibonacci, sequence, Tower of Hanoi, acquirements functions, queues, definitions, array representation, queue operation, circular queues using dynamic arrays, Dequeue, priority queue, amazing problem, multiple stacks in queues, programming examples. A linear linear array, insert and delete elements are at any place in the list, beginning and middle. One wants to restrict insertion and deletion take place only at the beginning or end of the list, not in the middle. Two data structures, stacks and queues. Stacks is a linear data structure, an ordered collection of items in which items may be added or removed only at one end. Last item to be added onto the stack will be first item to be removed. Last in, first out. Other names of stacks: piles, push down list. Ways of simulating recursion is by means of stacks only. Stack operations: elements are inserted or deleted only at the one end, called top of the stack. Various operations performed on the stack: push, used to insert an item onto the stack; pop, used to delete an item from the stack. This term used only for stack, not for other data structure. Overflow, check whether the stack is full or not. Underflow, check whether the stack is empty or not. Postpone decisions. Stacks are frequently used to indicate the order of the processing of data when certain steps of the processing must be postponed until other conditions are fulfilled. A is the main program, B, C, and D are the subprograms called the order given. The element may be popped from the stack only in the reverse order of that in which are pushed onto the stack. Array representation of the stack will be a while list of available nodes, free nodes were removed from the beginning. Now new available nodes were inserted only at the end, beginning only. This while list was implemented as a stack. Stack may be represented by means of one array list or a linear array. Top equals to 0, top equals to null. Stack is empty. Stack ABC 1 to 7 is max. Top will be at the position 3. Linear array stack. Pointer variable is top and variable is max. Then creation. This function implemented as a single dimensional array. S of stack size symbolic constant. Array used to hold the elements of stack. Defined as hash defines stack size 5. Int s of stack size. Push stack comma top comma max comma item. If top equal to max, then print overflow and return top equals to top plus 1. Set stack of top equals to item, return. Then pop stack top item. If top equals to 0, print underflow. Set item equals to stack of top, set top equals to top minus 1, return item, minimizing the overflow. Underflow depends exclusively upon the given array and the group input data. There is no direct control by the programmer. Overflow depends upon the arbitrary choice of the programmer for the amount of memory space reserved for each stack. This choice doesn't influence the number of times overflow may occur, reserving a great deal of space for each stack will decrease the number of times overflow may occur. Expensive use of the space if space is seldom used. Reserving a small amount of space for each stack may increase the number of times overflow occurs. Reversing a small amount of space for each stack increase the number of times overflow occur. Time required for resolving an overflow such as adding space to the stack may be more expensive than a space saved. Technique developed which modifies the array representation of stack may be more expensive than the space saved is so that the amount of space reserved for more than one stack may be efficiently used. Stack A within 1 element, stack B within 2 elements. If further requires 2 stacks, overflow occur either stack A contains more than n1 elements or stack B contains more than n2 elements. Instead, single array stack n is equals to n1 plus n2 elements. Operations of push and pop need to be modified. Stack 1 bottom of A grows to the right. Stack n bottom of B grows to the left. Overflow will occur only when A and B are together, have more than n is equals to n plus 1 elements. Decrease the number of times overflow occurs even through not increasing the total amount of space reserving for 2 stacks. Applications of stacks, conversion of representation expressions. Mathematical expression using Enqueue expression convert into equivalent instruction by compile using stacks. Evaluation of expressions. Arithmetic expression can either in the postfix form or the prefix form is easily evaluated. Recursion. A function which calls itself is called recursion function. Top is equals to 1 and status equals to 0. Void push into stack of this int item. Top equal to max minus 1. Printf stack overflow. Else stack plus plus top equals to item status plus plus. Then if pop of stack of I int item del, if top equal to minus 1 stack underflow item del is equals to top, stack of top minus minus status minus minus popped element is item del. Void display will be int stack int I. If top equals to minus 1, printf stack is empty. Else printf stack contents are I equals to top, I is greater than or equal to 0, I minus minus. Printf stack of I. Stack using dynamic arrays. Disadvantages of static array: maximum size of the stack should be known during the compilation. Once the size of a stack is fixed during compilation, it is not possible to alter the size of the stack during execution. Overcome by dynamic arrays. To start, let us assume the stack size is 1 int stack size equals to 1. Don't define stack size as a constant using hash define, because using dynamic arrays may increase stack size to accommodable more elements, so it must be a variable. Using dynamic array, once the stack is full, can increase the size of the array during execution and insert more elements. Expression: the sequence of operators and the operands that reduces to a single value after evaluation. Sequence of operators and operands. Infix: it is an expression if an operator is in between two operands. It can be parent. Postfix: in an expression if the operator follows two operands. Parenthesis expression. Unparenthesis expression, also called as suffix or reverse Polish. Prefix: in an expression if an operator precedes two operands. Unparenthesis expression, also called as Polish expression plus AV. Property of Polish notation: the order in which the operations are to be performed is completely determined by the positions of the operators and operands in this expression. Precedence of the operators or precedence rules that determine the order in which different operators are evaluated. During evaluation, if two or more operators have the same precedence, then precedence rules are not applicable. Go for associativity. Associativity of the operator: the order in which the operator with the same precedence are evaluated in an expression. Left to right association. Left association. In an expression, if there are two or more operators having the same priority are evaluated from left to right, then the operator are called left associative operator. While evaluating postfix or prefix expression, no need to worry about the precedence of the operator and the associativity of the operator. Whereas while evaluating infix expression, know the precedence of the operator and whether the operator are left associative or right associative. So convert them from prefix to postfix or infix to prefix. This is not standard. Some languages perform exponentiation from right to left. Infix to prefix. Infix to prefix, we do it as, for a bracket thing, we have plus AB, then star C, then star plus ABC. For bracket thing, we have star BC and plus A star BC. A plus B will become plus AB, then minus CD, then the slash will come left side. So for this, the inner bracket is B minus C, so it becomes minus BC. Then we have this multiplication symbol that we are taking. Then that will be star minus BCD, then plus A star minus BCD power E plus F. So this becomes power of this E plus F power to the E, so that becomes left side. Then we should add F. So this is all about powers. So x power y power z minus m plus n plus p by q can be written as x power y power z. We have it as, first we go with the x power y z, then power comes this side, power x power y z, then minus comes this side, then plus comes this side, then into, sorry, then also plus, then pq. Plus we will be doing for everything, so that comes initially. Division only we are doing for pq, so that comes behind p. Then a plus b, then all this order of operands are same. Transforming infix expressions to postfix expression. Let q be an arithmetic expression written in infix notation. Uses stack to temporarily hold operators and left parenthesis algorithm infix to postfix. One is push on bracket onto the stack and add this at the end of the queue. Then scan away from the left to right and repeat step 3 to 6 for each element of queue until the stack is empty. When operand is encountered, add it to the P. If a left parenthesis is encountered, push it onto the stack. If an operator is encountered, then repeatedly pop from the stack, add to P each operator on top of the stack which has the same precedence as or higher precedence the operator. Add operator to the stack. End of if a right parenthesis is encountered, then repeatedly pop the stack. Add to P each operator on top of the stack until a left parenthesis is encountered. End of end of step 2. Exit. The postfix expression P will be constructed. First push stack. This we encountered a operand, so A will be expression in the P. Then plus is encountered, that will be adding on to the stack. Then we encountered a bracket. Then B operand, that will be going to the expression. Then multiplication star. Then C comes to expression. Then minus, multiplication is higher than minus, so multiplication goes to the popped. Then minus, then bracket open again, T comes to the expression, divided symbol, then comes E, then comes this arrow. Arrow is nothing but power. Arrow is nothing but the power. Power is greater than the division symbol, so it is taken onto the stack. Then comes F, then bracket will be closed, then power, then slash, then bracket close. Then comes multiplication, minus. Multiplication is greater than minus, so it can be put onto the stack. Then comes G, then we kept G, then again bracket closed, so we popped everything. Then we have this H, we popped multiplication and minus. Then we have multiplication, which will be added on to the stack after plus. Yeah, because multiplication is greater than addition, it can be added onto the stack. Then comes H, then comes nothing, then pop everything. Here in this same thing we have infix to postfix. Here it will be done by like this. Postfix expression will be like this. Then M minus N plus PQ, divide, then plus. Then you can take this as an example. Another example, use two precedence functions f and g, contains the precedence values of symbols on top of the stack. G contains precedence values of symbols input string, that is 2, 4, 5, 8. Precedence function f, precedence function G contains the precedence values of the symbol in the input string, contains the precedence values of the symbol in the top of the stack. For top of the stack, precedent value is 2, 4, and for this is 5. Operands will be at 8, and bracket is 0, null for another bracket, and hash will be -1. Precedence for input will be 1, 3, 6, 7, 9, 0. Associativity will be left for everything or right for power. If an operator is left associated, stack precedence will be value is greater than the input precedence. If an operator is right associated, stack precedence will be less than the precedence value. During conversion order, it will be like this. This, like this. Then postfix to infix. If the scanned character is an operand, push it onto the stack. If the scanned character is operator, first operand operator, then second operand. A everything will be pushed onto the stack. Operand, push it to the stack. Everything will be pushed onto the stack. The scanned character is an operand. Then it will be D E power, so D power E. Then C star D power E. Then comes by B divided by C into D power E. Then prefix to infix. Reverse the prefix expression if the scanned character is an operand. Push it onto the stack. If the second character is an operator, reverse the operand. Pushed onto the stack. A minus B slash C star D this thing and E. Reverse the operand. Postfix to prefix. If the scanned character is an operand, push it onto the stack. If the scanned character is operator, take two operands from the stack. Prefix the operator. Prefix to postfix will be reverse the prefix expression. If the scanned character is an operand, push it onto the stack. If the scanned character is an operator, pop two operands, reverse it, concatenate with operator. To evaluate an arithmetic expression written in the infix notation, convert the expression to postfix notation, evaluates the postfix expression. The stack is the main tool to accomplish the above given tasks. Evaluation of expressions. Operators with highest precedence are evaluated first. Expressions are always evaluated from the innermost parenthesis expression first. Evaluation of the postfix expression. Consider P is an arithmetic expression. Add a right parenthesis at the end of the P. Acts as a sentinel. Scan P from left to right and repeat step 3 and 4 for each element of P until the central is encountered. If an operand is encountered, put it on the stack. If an operator is encountered, then remove the top two elements of stack where A is the top element and B is the next top element. Evaluate B operator A. Place the result back to the stack. End of if, end of step 2. Set value equal to the top element on the stack. Exit. To simplify the task, assume expression contain only the binary operators plus, minus, into, slash, modulo, and the operands in the expression are single digit integer. When an operand is pushed on the stack, its ASCII value will be pushed. Since an operand symbol is initially a character, want to push the corresponding integer value achieved by subtracting not 48 in decimal. Okay, from an operand 48. Symbol 0. The above statement takes the ASCII value of the symbol to subtract the ASCII value not, which is 48, from it. Example symbol 1. 1 has ASCII value of 49. So the statement symbol minus not produces the output number 1. 49. Okay, 62 by 3 minus 44 2 star plus, so that will be 6 by 6 2 by means 6 by 2, that will be 3 taken into the stack. Then minus came, 3 minus 3 0, then 4 0 4, then 2, 4 into 2, that will become 8. 0 8 will be there on the stack, then 0 plus 8, answer is 8. This is invalid expression. Why? Because 8 by 2 is how much? 4. Then 4 3 minus is there, 4 minus 3 is 1. Then 1 4 2 is there, 4 2s are 8 1 9 will be left, like that. No operator exists. Insufficient operator. Then if you try to do all this, you will get the results. Try doing it homework. Then recursion procedure. P is a procedure containing either a call statement to itself or a call statement to the second procedure that may eventually result in call statement back to the original procedure P. P is called a recursive procedure so that the program will not continue to run indefinitely. Two properties. There must be certain criteria called base criteria for which the procedure does not call itself. Each time the procedure does call itself, and directly or indirectly, it must be closer to the base criteria. Recursion function. The function is said to be recursive defined if the function definition refers to itself. Two properties. There must be certain argument called base values for which the function does not refer to itself. Each time the function does refer to itself, the argument of the function must be closer to a base value. Fortran COBOL doesn't support recursion. Factorial. The product of positive integers from 1 to n factorial. N factorial is 1 2 3 and then so on. 0 factorial is 1. 1 factorial is also 1. So n is equals to n into n minus 1 factorial. N is 0. If n is greater than 0, n factorial is equal to n into n minus 1. For suppose now we have to consider 4 factorial means 4 into 3 factorial, 3 into 2 factorial, 2 into 1 factorial, 1 into 0 factorial, which becomes 0 factorial is 1. So then what does it do? 1 factorial is 1 into 1, multiplies the things, then level 7, level 8, level 9, it gives the value 24. After this, algorithm for factorial will be if n is equals to 0, then set factorial equals to 1 and return. Set fact is equals to 1. Repeat for k is equals to 1 to n. Set fact is equals to k into fact. Return fact of k minus 1. So algorithm for this iterative will be like this. For k is equals to 1 to n, set fact is equals to k into fact. Then for recursion we have if n is equals to 0, then set fact equals to 1 and return call factorial of fact comma n minus 1. Set fact equals to n into fact. So then return. Original execution of procedure P is assigned level 1. The depth of recursion is recursive procedure P where the given set of arguments refers to the max level number of P during its execution. Fibonacci sequence F naught is 0, F1 is 1. Then this 0 plus 1 will be 1. Each succeeding term is the sum of the two preceding term. So base case will be consisting of two terms. That is f naught is 0, then f1 will be 1. Algorithm for Fibonacci sequence fib of n. If n equals to 0 and rn equals to 1, then set fib equals to n. Return. Call Fibonacci of fib of n minus 2. Then fib 2 is fib 2 comma n minus 2. Set fib equals to fib 1 plus fib 2. Return. Algorithm for Fibonacci fib n. That will be set f fib of 1 equals to 1, fib of 2 equals to 1. Repeat for L equals to 3 to n. And for set fib of L equals to fib of L minus 1 plus fib of L minus 2. Return. Iteration evaluating from bottom up. Recursion evaluating from top down. Bottom to up. Then Ackermann function is a function with the two arguments each of which can assign any non-negative integer 0, 1, 2. This function is defined as follows. The use of the Ackermann function was to show that there are functions which are not primitive recursive which cannot be compared by using only for loops with predetermined upper limits. If m equals to 0, then a of m comma n is n plus 1. If m is not equal to 0, n is not equal to 0, then a of n comma n is a of m minus 1 comma 1. Base criteria are the pairs. If m also not equal to 0, n also not equals to 0, then a of m comma 1 is equal to a of m minus 1 comma a of m comma n minus 1. Base criteria are pairs. Example 1 comma 3, which requires 15 steps to do that. Example 1 3. 1 3 will be a of 0 comma a of 1 comma 2. A of 1 comma 2 will be a of 0 comma a of 1 comma 1. A of 1 comma 1 is a of 0 comma 1, a of 1 comma 0. Then a of 1 comma 0 is equals to a of 0 comma 1. A of 0 comma 1 is 1 plus 1, that is 2. Then it comes up with 1 comma 0, that is 2. Then 1 comma 1 is 0 comma 2, that is 2 plus 1 is 3. Then again 1 comma 1 is 3. 1 comma 2 is 0 comma 3. Then 3 plus 1 is 4, which requires 15 steps. A of 1 comma 3 is 4 plus 1, that is 5. Then we have a thing called Tower of Hanoi. 3 pegs A, B and C. N is the number of discs with decreasing size. Move the disc from peg A to peg C using peg B as an auxiliary. Rules: only one disc may be moved at a time. At no time can a larger disc be placed on the smaller disc. If n is 3, 7 moves that is A to C, then A to B, then again the same way exists. N is equals to 1 mole. N is equals to 2 means 3 mole. Formula is 2 power n minus 1. 2 power n minus 1 moles. Queue. A queue is a special type of data structure, an ordered collection of items where elements are inserted from one end and the elements are deleted from the other end. The end at which new elements are added are called rear. The end from where elements are deleted called front. So it follows first in first out principle. Types of queues based on the method of insertion and deletion: linear queue, orderly queue, circular queue, double-ended queue, it is Dequeue. Since queue elements are stored in the linear order, it can be implemented using arrays and linked lists. Example of queue computer science occurs in a time-sharing system in which programs with the same priority form a queue while waiting to be executed. Array representation: front, rear point will be inserting. From the front we are deleting. Queue operations: insert element is inserted at the rear end. Delete elements are deleted from the front end. Overflow: when the queue is full, try to insert an item, that's overflow. Underflow: when queue is empty, try to delete an item, that is underflow. Define the queue size 5. This is a systematic constant and specifies the maximum number of elements that can be inserted into the queue and queue size. Queue is an array which is used to hold the elements of the queue. The variable front, rear are associated with the array queue and holds the index of the first element and the index of the rear element. Def is equals to 0 and R is equals to -1. Queue is empty, no elements in the queue. If rear equals to queue minus 1, queue is full. If then rear is equals to rear plus 1, queue of rear is equals to item for inserting an item. If front is greater than rear, then you can say queue is empty. Item queue front equals front equals to front plus 1. Printf item. Display: for I is equals to f, I is less than or equal to rear, I plus plus. Printf queue of I. Disadvantages of the linear queue: after deleting the element, the space cannot be reused. Rear insertion is denied even if the space is available at the beginning. Overcome by two methods. First method: assume queue is full. After deleting the element from the front end, move the entire queue to the beginning of the array, changing the front and rear accordingly by shifting the data in costly in terms of computer time if the data being stored in very large. This method is not recommended. Second method, circular representation. Increment rear by 1. Perform the modulus operator. Q is circular, so it should be 0. Rear is equals to rear plus 1 modulo Q size. Four plus 1 is 5. Modulo 5 will be 0. If it is something not 0, then it will be incremented. Increment front by 1. each time an item is deleted. Front is equals to front plus 1 modulo queue size. In circular queue, element of given queue can be stored efficiently in an array so as to wrap around so that end of the queue is followed by the front of queue. Circular representation allows the entire array to store the elements without shifting any data within the queue. This is an efficient way to implementing queue. Using the values of front and rear, it is very difficult to store, say, when queue is full and when queue is empty. Use variable count, which keep the track of number of elements in the queue. When no elements are there in queue, the number of elements will be 0. Hence, count is initialized to 0. Hash define queue size 5. Int q of queue size, then int f is equals to 0, int r is equals to -1, int count is equals to 0, void insert int item, int rear, int queue, int count. If count equal to queue size, if count not equal to queue size, if equal to queue size, circular queue is full. Else rear is equals to rear plus 1 modulo queue size. Queue of rear is equals to item count plus plus. The values are being changed. They should be declared in pointers. Void delete int front, int queue, int count. If count equals to 0, circular queue is empty. Otherwise, item is equals to queue of front. Pf is equals to related item is item. Front is equals to front plus 1 modulo queue size. Count minus minus. Then displaying this, we have front, queue, and the count. If count equals to 0, circular queue is empty. Else, contents of the circular queue are, for I is equals to 0 is less than count I plus plus, printf percentage dequeue of front. Front is equals to front plus 1 modulo max. Circular queue using dynamic arrays. Once the size of the queue is fixed during compilation, it is not possible to alter the size of the queue during execution. Overcome by dynamic arrays. To start with, assume queue size is 1. Int queue size is 1. Using dynamic arrays, once the queue size is full, increase the size of the allotted memory during execution to insert more elements. After incrementing the size of the queue, content have to be readjusted. Front less than rear. An item can be inserted into the queue by incrementing rear by 1. Then insert and update count by 1. Case 2, if front is less than rear, then increment the rear position by 1. If front is greater than rear. To get the proper circular queue configuration side, the elements 30, 40, 50 in above queue to right by 1 position. Queue size is 6. 4 down 2, then -2. Queue size -2 down to front. F is greater than R is equals to queue size -2. I is equals to queue size -2 then I is greater than front, I minus q of I plus 1 equals to I. Then front plus rear is equals to rear plus 1 modulo q size. Q of rear is equals to item. Then we have to insert. Double-ended queue is a linear list in which elements can be added or removed at either end but not in the middle. Dequeue is maintained by a circular array Dequeue with pointers left and right, which points to the two ends queue. The Dequeue left null used to indicate that a Dequeue is empty. Three variations: input restriction Dequeue, output restriction Dequeue. Input restriction Dequeue allows insertion at only one end of the list but allows deletion at the both the end. Output restriction queue allows deletion at any one end but allows insertion at the both the ends. Left 4, right 7, like that. Priority queue. A priority queue is a collection of elements such that each element has been assigned to a priority and such that the order in which the elements are deleted and processed comes from the following rules. An element of highest priority is processed before any element of the lowest priority. Two elements with the same priority are processed according to the order in which they have arrived. Then the prototype of the priority queue is a time sharing system. Programs of higher priority are processed first and programs with the same priority form the standard queue. Ways of maintaining a priority queue in memory. One uses a one-way list, other uses multiple queue list. Insertion and deletion depends on the representation that one chooses. One-way list representation of the priority queue. Each node in the list will contain three items of the information. One is information, data, then the priority number and the link number. A node X precedes a node Y in the list 1 when X has highest priority than Y, or 2 then when both have the same priority but X was added to the list before Y, means that the order in which one-way list corresponds to the order of the priority queue. Priority number will operate in usual way. Lower the priority number, higher the priority. Property. Element in the queue that should be processed first always appears at the beginning of the one-way list. It is very simple to delete and process an element from a priority queue. Algorithm deletes and processes the first element in a priority queue which appears in memory as a one-way list. Set item is equals to info star. Delete first node from the list, process the item, exit. Addition is complicated because to find the correct place to insert the element, algorithm adds an item with a priority number and with a priority queue which is maintained in memory as a one-way list. Traverse the one-way list until finding a node X whose priority number exceeds n. Insert them in front of the node X. If no such node is found, insert item as the last element of the list. Array representation of the priority queue. Another way to maintain a priority queue is memory user separate queue for each level of priority. Each such queue will appear in its own circular array and must have its own pair of pointers, front and rear. Two-dimensional array queue can be used instead of linear array. If each queue is allocated the same amount of space, front of k, rear of k, contain the front and rear elements of row k by of q, row that maintains the queue of elements with priority number k. Keep track of node address preceding the node being accessed. Algorithm deletes and processes the first element in priority queue maintained by a two-dimensional array. Find the smallest k such that if front of k is not equal to null, delete and process the front element in row k of q. Adds an item with the priority number m to the priority queue maintained by two-dimensional array q. Insert item as the rear element in row m of q. Exit. That's it. Thank you for watching. Do like, share, and subscribe to my channel.